Mr. Gabe Dagani, he is the director of GPU software at Samsung Austin Research Center. He has over 20 years of experience in 3D graphics, video games, and embedded systems. He's responsible for developing the software set that goes into millions of phones every year to support all graphics rendering on Samsung Galaxy phones. With that, I'll turn it over to Dagani. Thank you.
Thank you. Thank you, Ms. Dr. Peoples. How's it going? No, it's morning time, so okay. I'm going to talk a little bit about what I do, and I'm also going to go through an engineering case study with you guys just to kind of talk about the different challenges that we've experienced in industry. And I really am passionate about what I do, so hopefully this comes out in the presentation. Let me see. So the very first thing, and I don't want to talk down, but I work on GPUs. I talk to a lot of people, so the question is, what is a GPU? I think everybody knows by now, graphics processing unit, a lot of math to try to make pretty pictures. It's also being used for ML and every other SIMD type of workload out there. More importantly, a lot of people hear about GPUs, they don't realize they're just one piece of an SoC. Do you guys hear the word SoC a lot? System on a chip, and that's kind of what all chips are now. There used to be a bunch of chips on a board, now they've sucked them all into the same die. And so when we spin out a new product, which we do multiple times a year, the GPU is one of the bigger pieces next to the CPU and the camera and all this other stuff. And so that is kind of what my team works on. Not only that, but we are primarily focused on edge rendering. Edge rendering is making everything you see here, everything from portable game devices, foldable phones, regular phones, VR, and tablets. I've also worked on, let's say, automotive infotainment, you know, the GPS in your car or the cluster. All this stuff requires rendering, and it all has a lot of interesting constraints. Here's a blast from the past. Has anybody ever seen this device before? It's a, yes, good job. You get the nerd of the week. This is a Star Trek tricorder. This is from the next generation. This is when I was a kid. We used to watch this show back in the 80s and 90s. And so I bring this up because we always have science fiction leading the way to tell us what we're going to be doing in the future, right? And obviously the tricorder is our modern day cell phone, right? Has anybody ever heard of the holodeck, part of the Star Trek canon? It's basically this holographic room that you can be anything and do anything, which is kind of leading into what we're calling today virtual reality, right? Now, I only want to bring up virtual reality. I work on it adjacently, like Samsung does have virtual reality headset that they just released, but I think it's probably one of the hardest problems out there right now. And so I want to talk about why it's such a hard problem, and that's kind of the focus of my talk. And then I'm going to do a little bit of background on rendering, a little bit of background on engineering and other things, but I really just want to think about what it means to be an engineer and working on these kinds of devices. So one premise is concepts will temporarily fail without the right capability. You have the early VR in 1950, where somebody just threw a screen up in front of their face. And then you also have the early Apple Watch, right? Both of these things were great ideas, but they didn't have what it took at the time to make it really a good product. And so edge rendering is about working under tight engineering constraints. Here's a modified Maslow's hierarchy. You guys know what Maslow's hierarchy is? It's the things you need to be satisfied with your life. And obviously you have the normal ones, but you also have Wi-Fi and battery, right? That's a good phone joke. And so let's do a case study on XR. I talk about VR. A lot of people have probably heard of XR, but what is XR? XR is kind of this amalgamation of VR, AR, and MR. So augmented reality, digital layer over physical stuff. Mixed reality, you can have like little Pokemons in the corners, also the real world, so it's mixed. And then VR is completely synthetic. Okay, so all of these things have similar problems. AR is the hardest. Actually, mixed reality is the hardest. AR, you're just putting overlays, but mixed reality, you're trying to interact with what's going on around you. So I'm going to go over about 7 categories, can't count, of what are the product constraints you want to think about when you create something like, and I'll give you all the slides. Don't worry about taking a lot of notes. Just enjoy, and I'll give Dr. Peoples my slides. First thing is display. So hopefully a lot of you guys have heard the terms resolution and frame rate. Resolution is how many pixels, and frame rate is how fast the scenes change, how many frames you get per second. The question I have is how many pixels are enough pixels? Okay, it's a very interesting constraint not many people think about. And you can go back to just first principles. You can say that perception is it's a part of distance versus viewing angle. And so you can see that most people can't focus closer than 4 inches. That's a nice, good constraint because it means we don't have to focus on that. Of course, VR changes that, but they have pancake lenses. We'll go into that later. And then legally accepted vision is 2020 is around 900 ppi. And then like the max anybody's ever been able to perceive is around 2200 ppi. Now, those seem like random numbers. I'll get into what that actually means. So if you think about it, we're already kind of achieving these already. Reading a book with a Kindle already has 300 ppi. And at a foot, that's the max you can basically perceive. You can't get a better Kindle. It's a solved problem. You have using a laptop 2 feet away from you or something about, it's about 120 ppi. If you have a 4K, that's way killer too much. It's like 282. You could actually get away with 1080, no problem. Unless you're really like staring at it very close, it's plenty. Watching TV from 6 feet, 4K, more than enough. 8K, too much. In fact, that's why they made 8K kind of frowned upon in Europe because you're just wasting power for no perceivable gain. You have movie theater, which is the only time 8K actually does make sense. You're sitting 30 feet away from a huge screen at 100, let's say 100 inches, no, 900 inches. And it's about right. If you're going to get there, 8K at a movie theater is probably the only time you ever really need to see an 8K. Using a mobile phone, that's my thing. Sorry about the red. But basically what I'm trying to say is they're all fine. HD plus, you can get those on like $300 phones all the way up to like full quad HD plus, which is 500 pixels per inch. You can't even see that. It's kind of a waste of power. So I kind of think cell phones in this form factor solve problem. Then you have color perception. And this is something that can still kind of improve over time, like blacker blacks, deeper reds, HDR, non-HDR. And they base all of this based on physical feedback of the 3 different frequencies our eyes hone in on, as well as the rod of illumination or luminance at around 500. And so these are still important. And Samsung has a big monitor division that kind of tries to figure out how to get that, you know, everything from micro LED to OLED to God have whatever. So this is still an interesting problem. We could probably still make some difference here. And now if we're going back to VR, we think about what about field of view? If you've tried, how many of you guys have put on a VR headset? Most of you? And one of the main things you think is that the field of view kind of isn't great. One of the things is if you're going to have maximum field of view, the interesting thing is you have this thing called a nose that actually blocks some of the vision. So your brain has to compensate. But overall, even your periphery is about 200 to 250, 270 degrees in a perfect situation. And if you look at like, I just grabbed this off the internet, the different things out there, like the Quest, Oculus Quest only gives you 90. That's why it's kind of sad. You have the Vive, the Valve Index, which just got replaced by another Valve device, and then the Pimax. And then you can see that they're getting closer and closer and closer. We can still improve. But for the most part, until we get that, you don't want to be distracted. You want to be immersed. And so this is something we can still work on. XR screen resolution is a little bit different from just regular flat screen resolution because you're playing with the periphery. And then you also have a different measure because you're so close that the pixel count actually does matter a lot more. And human fidelity can detect about 60 ppd, and in most cases they can get around 40, and they have to do a lot of tricks to make that improved. One of the tricks they do is something called foveation. Does anybody know what foveation is? What's foveation? Right, like you have a way less perceptible ability to see what's on the very periphery of your vision. And so why spend a lot of compute on that? You can do multiple things. One is you can render less on the outside, make it like coarser and finer grain in the center. Another thing you can do is this warping, which is really interesting, which is what most of the VR goggles do. They do something called the pancake lens, where they take your normal grid of pixels, they highlight the importance, which is where they're growing the center and making the smaller outside, and then they're de-warping it here, and it looks, and then it looks clean, but what you're actually doing is you're shoving a lot more detail and a lot more of those pixels in the center, and then on the output of your display controller, you're actually mapping something that looks like this, and then when it goes to the pancake lens, it comes back normal. So it's like you're dewarping and you're warping and dewarping at the same time, but you're shoving a lot more pixel density in the center to kind of make use of the physiological perception importance map. So that's pretty cool. I'm going to go away from just resolution. I'm going to talk about what makes a picture move. I know this might be, I actually love this kind of stuff, just thinking about things that you take for granted. So the question is, what is the frame rate of your eyes? Does anybody know? It's actually kind of a trick question. There really isn't a frame rate for your eyes. It is an accumulation over 10 hertz. So your eyes kind of collect light over 10 hertz or 10 tenths of a second. And then whatever light you see is kind of how you amalgamate that image. So in any given time, you're seeing 10 hertz previously all the way up to the present. It's kind of weird. You're seeing the past, but you're also seeing the present at the same time. It's all together. Now, it's very quick, so we don't perceive it, and we're actually pretty slow, so that's fine. But it's also an interesting thing that you can take advantage of as an engineer. The other interesting thing is something called the critical flicker threshold, which means that we actually are very sensitive to our periphery movement only. We can't make out details in the periphery, but you can make out movement. And the reason is because if you think about the whole hunter scavenger in the wild, you want to kind of detect movement, see if there's like a mountain lion, or if you're trying to hunt for something, you want to see if anything's moving in the brush, And so our bodies have this ability to kind of see very fast movement, but unclear, almost like you're just doing a motion detection in the sides. And that's something you also have to pay attention to, because it could be either good for your immersive experience or it could be taking away from it. So if you look at what refresh rate looks like in the history of like computer vision or computer display, 4 frames rates, you have 8 frame rate and 24 rate, you kind of see the smoothness difference. But if you look at like back in the day, they had 16 frames per second for silent movies back in the 50s, 40s. Then you went to 24 frames per second, which is actually the cinema standard today. And it's almost because we've gotten used to it so much that if you go any faster, it feels weird. 30 frames per second is Nintendo type console graphics, and also on your mobile phone, older mobile phones. And then 60 frames per second is the absolute minimum for any kind of shoot 'em up FPS shooter type of thing. And so 60 frames per second is the bare minimum. And when we are putting out a phone, we have to play all the latest games like Genshin, Honkai, Call of Duty, 60 frames per second. If we don't hit that, then it's actually a fail. So we're talking about XR. If you read, here's just one sample point. I'm not saying this is the expert, but this is just one sample point. And their claim is that 120 frames per second is about what you need for immersion without getting that nauseated feel. So it's a pretty high quality. It's a pretty high bar. Okay, we've talked about display. Let's talk about computing. So there's 2 XR use cases. One of them is you have this umbilical and you're hooked into a very fast computer. And then there's another one where it's standalone, where everything's built into the device that sits on your face. We're going to talk mostly about standalone because it's a harder problem. And this whole exercise is talking about how hard engineering constraints can be. Latency. What is latency? Anybody want to? What's just general definition of latency? We use it all the time. Do we really understand what it is? Yeah. Right. And so when you have an XR headset on and you move, if there's any delay, it's going to make you dizzy. It's almost like you're drunk or something. Not that anybody's ever had that experience. And so what you want to do is you want to limit that latency as much as possible. And a given like normal 60 frames per second, each frame has to render within like 8 milliseconds, right? And so just to give you kind of typical refresh rates for head-mounted displays, HMDs, 90 frames per second would be 11.1, but 120 would mean 8.3. And you actually have to render 2 different screens, and you have to do it really, really fast. One way to hide this is something called reprojection, which is where you draw a picture bigger than what you can see, and then you use motion sensors in the head-mounted display. So if you move, it just it slides the image in front of your display without re-rendering it. And so it's almost like you're panning on an existing thing very quickly, which gives you the illusion that you're moving within it without having to wait for that latency. Does that make sense? So it's like a near round trip in order to hide some of the latency going all the way back to a computer. Another trick is, we used to call it chasing the beam. Back when TVs had a raster display, they had like electron beam and you were going like this. And I'm old enough where like when I first started working, we had these CRTs, these computers with these shooting lasers at your face. And we had to chase the beam because if we try to do something called double buffering, which is draw a picture, render a picture, and then swap, right? Ping pong buffers. If you try to do that, it was too slow, so you had to chase the beam. Here, chasing the beam is actually even slower, so you have to break up the screen into 4 different pieces in order to allow you to hide some of the latency even inside a single frame. That's how fast, or the low latency, the very little tolerance on latency is basically what I'm trying to say. Okay, so computing. Perception. Now, this kind of goes into Dr. Peoples' area where it's a lot of computer vision. You want to have a good immersion experience. A lot of computer vision is going into VR. You have everything from hand tracking, you have everything from eye tracking, night vision, trying to understand what's going on around you so you're not running into walls, and also trying to understand how fast you can move the display and give the computer fusion data back in order to improve that immersion experience. One of the most important parts of that sensor fusion is what they call it when you have a bunch of different sensors coming in and trying to munge the data together, is depth perception. You can do it. These are just 3 typical ways of doing it. Structured light, you put some kind of IR field on something, and then as it is, if there's something in front of it, those IR lines or patterns or hash marks are going to deform, and then you can tell the depth by that deformation. You also have time and flight sensors, kind of like a bat, like echolocation, but with light. You shoot something, as it comes back, you measure like the nanoseconds or milliseconds in order, and you can tell the depth based on that. The most popular way and the cheapest way, the way the Teslas do it, is you use stereo perception, where you have 2 different cameras, and this overlap, the difference in angle of perception on the overlap can tell you how far away it is. And these are all valid, and sometimes they do multiple of these just to get the depth perception even better. Another area that's important is movement sensing, where you have what they call an IMU, inertial measurement unit, inside of everybody has one. It's the thing that like allows Google Maps to tell you how fast you're going, or if you're stopping, or if you ever do those games where you're like moving the phone like this. You have a gyroscope, a magnetometer, and an accelerometer. Magnetometer is for compass, like where's true north. Accelerometer is self-explanatory, and gyroscope is kind of level. Okay, next area, battery life. In a typical cell phone, that's what I'm most familiar with, the most expensive piece on it is always going to be the display. That's why if you ever want to save your battery on your phone, you dim it. You can get twice the battery life. If you ever hit power saver, it's going to turn the dimming down. And depending on how fast the frequencies are, it's going to be the GPU and then the CPU. Typically, the CPU is on all the time, and the GPU is only on if you're doing like, heavy TikTok or video games or, other kinds of things. Modem takes 800. Depending on the distance to the tower, the closer you are to a cell phone tower, the less power it has to broadcast. You have Wi-Fi, also takes a lot based on the transfer rate. How much are you trying to download? And then, Bluetooth, memory, and RAM. So all of these things. So there's a little bit of when we make a phone, we have to think about like how long can your battery survive? So airplane mode, when you don't have Wi-Fi and the screen is on, you're watching a movie or something like that, maybe 800 milliwatts. Web browsing, 1500 milliwatts because you're using Wi-Fi. Low video gaming is 2.5 watts. That's like Angry Birds, or card games. Heavy gaming, it's like Genshin, it's gonna be almost 5 watts, right? Listening to music's almost nothing, 0.25 watts. And a minute phone call is about 1 watt. And so if you think about it, most flagship smartphones have about a 5,000 milliamp hour battery. And so for 24-hour usage, you'd need to average 200 milliamp hours So if you look at it, you say at 5 watts, we can probably play a video game for about 3, almost 4 hours. At like Angry Birds, you could probably play for 7.5 hours. And then idle, it could probably last for about 35 hours, which is just based on the math, that seems right, based on people's usages. Here's an interesting tidbit that I think about a lot. Memory usages are super expensive. You're hearing a lot about this with AI and ML, but on a phone, it's just as important, where like they created, they're doing a lot of trying to move processing into memory. Why are they trying to move processing into memory? Because a DRAM access is 1,000 times more expensive than a single compute operation, which means you can compute for 1,000 operations on integers, or maybe 100 operations on floating point, or maybe whatever, 100, 200, 20, whatever, 1,000 divided by 40, do the math, 250 times. And then SRAM accesses are also cheap. And so this, I mean, this is computer architecture, right? This is why you have L1 caches, L2 caches, SRAMs, because you're trying to save both time, latency, and power. So a lot of times it might even make sense. And these are in terms of nanojoules, picojoules, femtojoules. Very small, but they add up. Okay, use case. I'm not going to go too much into use case of XR. My personal opinion is it's not there yet, but it's very cool. And I think I applaud everybody who's going into MR to VR and XR, but I can't use it. It's like Pepsi. The first taste is great, but you can't finish a whole can, And so it's like that, but I've applauded. I think the vision for it, when they finally do get it right, it's going to be amazing, but we're just not there yet. Let's talk about comfort a little bit. I know it's one of those things people don't think about. So you have 3 major brands right now. Actually, Valve just released a new one, but you have the MetaQuest 3. Part of the design here is making it thin and light and close to the face to keep the center of gravity close to your face so you don't feel the weight on your neck, right? Apple did it a little bit differently. They did mount straps, but their actually biggest complaint is it's very heavy on the front, and that's why a lot of people are complaining about this one. And then you have Valve Index, which put a weight on the back to counterbalance the weight on the front, which can work. But it's all about neck strain. Like we already have the problem where we're staring down at our phones all the time, and you're getting like phone neck, and so this is just going to add to it. Another interesting thing is the #1 reason why phones can't go faster is because of thermals. Here's I think it's a NASA study. It says that skin temperature, any more than 45 degrees, you can't hold it for indefinitely. 45 degrees C. So if your phone gets anywhere near over 45, it starts to cause actual pain after 60 seconds because your hand starts to get hotter and hotter and hotter and still starts feeling pain. And then so if it was at 70 degrees, you could hold it for 1 second without feeling pain, right? If it was at 60 degrees, 2 seconds, and it comes down, and then somehow starting at 45 degrees C, it stops hurting. It might be warm, but it's not going to be like a lawsuit. So that's kind of interesting. And actually, that's one of the tests we have to run when we do something called DVFS, or dynamic voltage frequency scaling. We power back the phone to make sure that the thermals are always under 45 degrees C because you're holding it in your hand. And then last is cost. I'm just going to do the Apple Vision headset. This is on the web. Somebody did a teardown. The most expensive parts of is the screens. They have 2 screens. The second most expensive parts are the chips. Makes sense. And then it goes down to the radios, the actual metal hardware, the RAM, and the pancake lenses and the battery. The battery is actually pretty cheap. The reason why you don't see more battery in things like phones is because they get big and you want that slim phone feel, right? But it's actually not that expensive. And if you look at what Apple Vision was costing, it was like $3,500. Usually divide by 2 to get the bill of materials, and you can add the fractions there to figure out what it is. Similar to a cell phone, these are the phones that we make. This is a couple years old, but the processing and cellular is 35% of the cost. The display is 20% of the cost, camera 15%, so forth and so on. And a phone, something like $1,000, maybe $1,200. And so divide by 2 and add the fraction. So the summary of this case study is constraints help focus the effort on what's important. How are we going to make the customer happier? How are we going to make the experience better? And you kind of have to keep them all in mind while you're trying to make something that is cool. So I'm going to talk about my passion, my background at Samsung is we make the GPUs that render video games and everything else, including like running ML networks and things like that. Like the phone is becoming a pocket everything device. So here's a short introduction to 3D rendering, very short. I'm not trying to, I don't know what their background is, so I'm going to start from very high level and kind of go down a little bit. So 3D representation, everybody knows kind of what 3D is. You start out with 2D that you did in Algebra 1 with X and Y. You add a third dimension, X, Y, and Z. And then you have all these vertices, and based on their order in a list, you create triangles. Every 2.5 vertices is a new triangle. The next triangle shares the third vertice on the previous triangle, and you make these things called triangle lists. And if you do it right, it'll make these cool shapes. They are called meshes. And then as you get more details into the meshes, you get more detail in your objects. And so kind of digging down into that a little bit. So we have vertices. We know what vertices are. We have meshes, which is a group of triangles that are made into cool objects. And then you have transforms, ways to manipulate, warp, and a transform is really made up of the SRT, the scale, rotate, translate. So scaling, making bigger or smaller, rotating, obviously, translating, shifting, or panning. So the cool thing about matrix math is you can do all of them at the same time. You just put them in different spots inside the same matrix. You multiply that matrix by that mesh. Ta-da, it works. And then you get into the art part. Dr. Peoples works on textures. This is just what we call a texture map. Think of it like a car skin that you'd see on a Tesla, Cybertruck. You have your mesh. You have a texture that maps to that mesh with these things called UV coordinates, where they know exactly which vertice at different points you're going to pin this texture to. And then you get something that looks, reasonable. You have characters and animations where you build something called a skeleton. This is called the T-pose. And then you manipulate it using quaternions or also transforms against every joint in the skeleton. And then you're basically always telling people what is the difference between this pose and this pose. And then as you move, you're just adding differences, and every joint has an angle and a offset. Angle, offset, angle, offset, angle, offset, almost like robotics. We don't do this by hand anymore. Back in the days, they actually had animators like puppeteers. Now what you do is you have mocap or motion capture. You take a video with like 100 cameras of somebody doing something super cool like a ninja move, and then you map that capture to a skeleton, and then they have enough software now that this has been done for like 30 years. They can make that guy do whatever, and then you have this thing called an animation stream you feed into a character to make it do what you want. And so a lot of that's automated, and we still have animators that curate and tweak and make it look more lifelike, or maybe take an existing motion captures and change them a little bit. And ML and AI are actually going to help quite a bit with that. So it's an exciting area. Let's talk about the hardest part of graphics, which is lighting. So there's different types of lighting, and there's different types of cameras. So when you think of a camera, you think of, this is called a camera frustrum or a viewing frustrum, where it looks like a sideways pyramid. And this point is where the camera is. That last wall is the far plane. This is where we're going to stop recording. This is the near plane. This is where we're going to start recording. And then the outside walls is where we're going to clip anything that's not in it in order to save computing bandwidth. Like if it's not in our view, don't render it. It's kind of like I used to work on Madden football. And the nice thing is you only ever render mostly half the field at one time, because if you're in the middle of the field, you can't see behind you. If you're in the very corner of the field, you have to do it all. It's very expensive. But if you're in the middle of the field in the game, it's not too bad. Then you have different types of light. You have directional light, you have point lights, you have ambient light, and you have spotlights. And then you have two types of illumination. So light bounces. It's not just light hits something, you're done. Usually there's a primary surface and then there's a secondary surface, and then depending on the materials and the refraction of the materials, you're going to get different effects and even different colors bouncing off of different materials. And so you see global illumination is kind of a emphasizing the fact that we're all kind of in an ambient light. We're not all just seeing spotlights all the time like you're being investigated by the police. You're kind of seeing this general ambient light all the time. Give you an example. This first one is if you had 0 bounces on your light. You just had light coming through the skylights. This is what it would look like. It would look very weird. As you have marble surfaces that naturally reflect light, you're going to get this global illumination that looks more lifelike because that's how the world really works. Computers need instructions and they need them to be done in a very specific sequential way. This is the general graphics pipeline without going into too much. We start with the vertices. We connect them into specific triangles. We turn those triangles into fragments by laying them on top of a grid paper, which we call the screen, the pixel screen, the render buffer. And then we color them based on the lighting that we just talked about. Now, we can go into that later, and then we overlap them based on a depth buffer, a painter's algorithm, which is like you have something behind something and something in front of something. Therefore, you render the thing in front of something over the thing behind it, right? It's very high level. Here's another illustration of rasterization I like, where this is vector world, which is perfect and floating point accurate. And here is raster world, where you only have 2 million pixels on your screen, and you need to map that to that and make it look as good as possible. This is the most classical way of lighting. There's three components of lighting. It's called Phong shading, from a guy who published a paper named Phong. And so you have ambient, which is like the general backlighting. You have diffusion, which is where you start to see some of the normals hitting the materials, and you're starting to say that the diffusion of the light. And then here's the specular highlights of things that are basically direct on with the light. So if you hit something directly with the light, it's going to be the brightest. And especially on a very shiny material, we have we call specular highlights. And when you add them all together, you get the general look, you get the kind of diffuse look, and then you get the specular highlights. And it does a pretty good job for most situations. Also, as you guys have heard of ray tracing. This is where you're physically modeling light as it bounces around a scene. And somebody used to say ray tracing is like putting a supercomputer on each pixel and then telling it to go. And that's kind of what it is today. There's a lot of tricks to speed it up, but the idea is you're casting these light rays at a scene, and whenever it hits something, you tell it to report back and tell it what the material color is and what light has touched it. And you're modeling a scene. And it's very expensive, but the computers and the techniques are getting so good that you can actually do it on a cell phone. The first time, we were the first to put ray tracing on a cell phone, and it was in 2022. And so now we're 3 to 4 years past that. And so now we have video games out there with ray tracing. And the things that really thrive with ray tracing now are shadows, because shadows are very hard to do, because typically you had to cheat and do all of these other techniques to kind of pretend to have shadows. But with ray tracing, you can actually just model the shadows, and they look crisp and clear and good. The other thing that it was really hard in the past was something like reflections in a mirror. What you used to do is take a picture of the whole scene, map it onto a surface, but you couldn't do that every time because it was very expensive. So what you'd actually do back in the video game days when we cheated all the time is you would take that snapshot of the scene maybe once a second and then use it for the other 60 frames, and then just hope people didn't notice that the reflection was maybe a second old. But with ray tracing and reflections, it's actually a cheap operation, single bounce, and you kind of get a good view of what it should look like, especially with transparency reflections and things like that. Just very high level. One of the ways that we cheat is we use these things called bounding volume hierarchies. Have you guys heard of these before? They're a way to generalize and say, here's the root. The root is this beige box. And if you were to shine a line to this outside of this beige box, we'd say, throw away that ray. We're not going to do any compute on it. The minute you're in this, the next question is, are you going to need any of these blue boxes? If you're not, throw it away. Then you're going to say, okay, we're in a blue box or in one of these green boxes. If not, throw it away. And this actually will save you 30 to 60% of your compute. Very simple. They used to call them KD trees. Now they just call them bounding volume hierarchies. And there's a lot of science going into them. Whether you build them every frame, or you build them every few frames, or you take one that's built and you just adjust it. These are so important that without these, ray tracing couldn't work. Okay. I'm kind of done with my intro to computer graphics. You guys are now experts. I'm going to talk a little bit more about what I do. One of the statistics I like to talk about is the fact that since the beginning of time, the Commodore and the Atari 2600 and all these other things, there have been approximately 2 billion video game consoles in your living room built and sold ever. Seems low to me, but it's accurate. Last year, we sold 1.2 billion phones. So I would make the claim that your mobile phone is the most popular game console that ever existed. So that's what I work on. What's the difference between a mobile graphics pipeline and one that you would use on a desktop? A desktop, for most notebooks actually act more like mobile, but for a desktop, they have a PCI card and they have a separate memory GPU. And typically there's a lot of delay, but they're able to run extremely fast because they're plugged into a wall with a bunch of fans pointing at the GPU, right? And so the trade-off is that you have a discrete graphics card and you can basically burn it up, put a fan on it with water cooling and do whatever you want and you can get a lot of performance out of it. We can't compete. We're in your pocket and we don't want to burn a hole in your jeans. The mobile has a unified RAM architecture, which means the same RAM that's being used for your CPU is also being used for your GPU, which means that if you're not using the GPU, the CPU can use it and vice versa. There's also a nice thing that you can make use of, which is zero copy. Zero copy means that as soon as the CPU is done with it, it says it points to it in memory and gives it to the GPU, and there's no transfer cost. On a desktop, they have something called an aperture into RAM, or an aperture into video RAM, and you have to like point to that specific part, lock it, write to it, and then say I'm done, and then the graphics card can read from it, and there's like a handshake. And they get away with it because they're going fast enough and their frequencies are like 2 to 3 gigahertz, and that's great. But for mobile, we have to make a lot of trade-offs. The different mobile GPUs out there, I work on the Xclipse, which is it comes from the AMD RDNA 3 and 4 line. We bought that architecture and we're changing it for mobile. There's the ARM Mali, the Qualcomm Adreno, Apple GPU, the Imagination Power VR, which is in like Vivo, Oppo, and actually what the Apple is based on. NVIDIA Tegra, Vivante, and Broadcom all have GPUs. Broadcom's mostly like set-top boxes and things like that. Most of you guys have heard about Intel, Apple, NVIDIA, and AMD. But these are all the ones, since they're the most popular in the world because you have them in your phones all the time, they're actually the most popular also. So what makes a mobile platform? I like to throw out, let's call these speeds and feeds, because most people don't realize how powerful their cell phones actually are. For the Apple, it has 2 big cores that run at 4 gigahertz at maximum speed. For ours, we have 1 huge core that has 3.3 gigahertz. And then we have these things called performance cores, which are like, call them medium cores. We have 7 medium cores and 2 efficiency cores, which are like very small that you can run and keep the battery going, but you can do just like very simple stuff, web surfing, blah, blah, blah. And so it's like having 6 or 7 or 10 different engines in your car where you only use the engine you need at the time, almost like switching gears, because you don't want to take more gas or power or battery than you actually need. But when you do need it, you want to be able to use it all. That's what the big cores are. So one example is if you were to, in a game, you have to compile things called shaders. And you want to get it done really quick. You launch these cores, you turn them on, you turn them off as fast as possible, like a dragster. And you want to get that immediate feedback response, but you want to turn them off because they take a lot of power. Another interesting thing is you have these GPU cores, and these GPU cores are not nothing. This is running at about 4.6 teraflops. Flops is floating point operations per second. You have 5 teraflops, 4, 2.5, 2.3. And then the NPU doesn't do floating. I mean, it might do floating point 16 sometimes, or maybe FP8, but it's not a major floating point thing. It's mostly focused on integer operations. So there's a little bit of floating, but they usually measure it in tops, which is just operations per second, like I'm trying to remember what the T stands for, I don't know. But basically integer operations per second. And so you have a lot more power here, but at a lot lower precision. So when they're measuring things like 100 tops or 50 tops or 60 tops, it's like integer 8 operations. You have modems, Wi-Fi, and you're on the fastest bleeding edge nodes. In fact, the phones are the ones that pipe clean the fab and say, hey, 4 nanometer, 3 nanometer, 2 nanometer, however many angstrom, those always go on phones first. So it's pretty interesting. if you go into the history of gaming flops, the point I'm trying to make here is, the latest PlayStation Pro is at 16.7 teraflops. And then if you look at what we were just saying, is we have about 4 teraflops in a phone now, which is about the Xbox X. Now the difference is it's not really an Xbox, because if you had it at that frequency running at that same level, you'd burn a hole in your pants. But if you were going to run it for short speeds of time, then yes, you would have that same amount of power. Okay. I'm going to go into advanced topics and graphics. One of the areas we're really focusing on now is super scalar frame generation and denoising, kind of like the NVIDIA DLSS. So what this does is instead of rendering the whole screen, you render maybe a quarter or an eighth of the screen, then you use machine learning to scale it, like magnify it. And then you also do frame generation. Maybe you do motion vector estimation for what the next frame should look like, and you add a frame in between 2 frames. And then you denoise, because with things like ray tracing, it's like a stochastic model, and you're shooting all these rays, and there's points where you didn't shoot rays, and you have to like blur them and make it look sharp. So there's a lot of interesting things going on there. That's one of the areas of focus we're focusing on. Neural rendering. I don't know if you guys. Anyway, whatever. I like this slide. And so it's when you add computer graphics and machine learning together, you have neural rendering, and there's a lot of interesting topics. Dr. Peoples is working on some of them. Things like NeRFs, where you're taking a lot of images from around a perspective and you're generating a 3D model from points, and then point models, and then you're kind of being able to recreate the mesh from just sheer, I think they call it photography, grammetry, whatever they call the word. And then here's another area that we're really focusing on is neural texture compression, where you can get extremely good textures. You remember those things that we wrapped around the dog? With very high quality, like carpet is hard, velvet is hard, metal with rust is hard. All of those really complex materials are very hard to simulate with a single texture. Sometimes what they do is they'll do up to like 25 textures layered on top of each other with transparency to try to get that effect that you want with different lighting. And as opposed to doing all that work, we can basically take pictures and measure a bunch of different facets of it and then recreate it on the fly using an ML model. Here's a joke for me. When I was a kid, we had Transformers in school, and then Transformers in college, and now Transformers, right? And so there is a lot of interest in the Transformers we're doing today. A lot of phones right now are obviously making use of LLMs to answer your emails without you actually thinking about how to articulate it, to summarizing what you want to say or extrapolating and making you sound more intelligent. A lot of the harder stuff is going to be the pixel-based LLMs, the generative models that have to do with pixels, just a lot there. And so for the foreseeable future, we might do a little bit of the pre-processing on the phone, send it up to the cloud, get it back, but it's way too expensive to do a whole lot of that on your phone. Like if you did like a stable diffusion model and said, draw me a unicorn on a surfboard, it would take you like 45 seconds to get an answer back on your phone today. So if you're willing to wait, it's great. If you want to do WhatsApp and then say, hey, take this guy, put him in a mankini, you can do that for sure, but it's probably going to go up to the cloud. Okay, careers, I'm almost done. You guys have been very patient. So in the process of making a GPU, we are always kind of 3 years into the future thinking. Like right now we're planning for 2028 and 2029. And so we do marketing, requirements gathering. I do a lot of that. We go to different conferences. We see what's hot. We look at our competitors. We do some kind of, crystal ball gazing. Then we come back to our hardware engineers and say, this is where we need to be to stay competitive. And then we get pushback because things are always expensive. We only have so many resources and people and size of the die. And then, we do software, hardware, co-designs. We get these things called big rock features and small rock features, and we vote on them, and we try to see how much it's going to cost. We go into hardware architecture, hardware RTL design. You guys know what RTL is? Great. And then we have a whole RTL team. So Samsung Austin Research Center does everything. We have an architecture modeling team. We have an RTL team, a PD team, a DV team, full layout team. We do all the testing and then software validation, hardware validation, everything. And so I'm doing all the software side, so it's pretty interesting. We even do validation and emulation, where we take all of the RTL, we put it on a bunch of emulators using FPGAs, and we say, pretend to be the real chip, and then we're going to look for crashes and debug them using these things called wave dumps, where we're looking at all those waves, and we're seeing where things stop and they shouldn't stop. All right, physical design, device integration, and we tape out, we send it to the Samsung fab. Samsung has a fab. We're building one up the street in Taylor, $17 gajillion or whatever. I'm not really a part of the foundry. I'm a part of like the Cube Cadet, Cube Core, where we're just a bunch of dorks and a bunch of cubes, and we're just designing this stuff. But we send it down, we mail these designs to the foundry, then they make them, and then we get the chips back, and then we bring up the chip, like Frankenstein, is it alive? If it's alive, and it usually is, then we start putting all of our drivers on it, which is what I'm in charge of. We have tools, we have device productization, we have to run every game known to mankind. We have 3 to 5 million tests we run daily just to make sure that when someone makes a change, we have CI, CD to make sure they didn't break something else. And then we have application development, field application engineering, and trying to figure out why did it break. My software responsibilities look something like this. So 3 years in the future, we're feature specking things out, we're doing architecture, but we're actually also supporting old devices. So like you get an update on your phone, we have to update the Android OS, we have to make sure everything works, and we have to do performance analysis, make sure things aren't getting slower. We keep updating the OS every year, and then we do feature development and validation, and then we have package out. This is when the chip comes in, and then we feature tune, performance tune, and then we release it, and then we have maintenance in the future. So keep conformance healthy, keep performance healthy, and keep updating the OS. So this is real life. You don't just get a kick butt and move on. You actually have to maintain and make sure everything that you already made doesn't break. How do you do development when you don't have a device in front of you? A lot of that has to do with using architecture models. These are like C models where they functionally create what the chip does in small portions using a batch server farm, where each part of the GPU runs on a different thread, and then it's running, and it's literally doing everything exactly how the hardware would do it, and we call that a C functional model. And we also do GPU architecture models, which is a different model, which is saying, in general, this is how it's going to work. And if we made this instruction, or if we made that bus bigger, how would the overall performance for this workload change? We have a GPU software simulator where we are just making sure that the instruction sets are doing exactly what they're doing. And if we compile something, the assembly looks right. And then we have a hardware emulator, which is at the very end when the RTL or the design is very, very close to being polished and done. That's when we really start hammering it and making sure that it looks good before they send it to the oven, right? So careers in graphics, kind of talked about this already. I've been in most of these already. You have visual effects. I haven't been in that one. That's super cool. I did a little bit in video games where I've had people work at like LucasArts and DreamWorks and all these things, and they're working on these huge RenderMan type farms where they're just making sure that the light coming off the space cadet or the astronaut over here and the alien looks amazing, and they're using the fanciest, and it takes something like 30 hours to build one frame because they're doing all of this ray tracing to get it to work. You have rendering engine developer, people who work at Unreal and Unity and Blender and Godot. They all make the tools that allow people to make the video games. And actually, this is kind of where the world is going, where you're not going to, it used to be everybody goes home and makes their own renderer, like their own engine, their own game engine. But now people would rather tell a story than have to do all that technical stuff. So leave the technical stuff to these huge engine companies that just focus on it and then just build the game. Technical artists, these are the people that do the artistic stuff where they're making the models, they're making the scenes, they're making the textures, they're making the animations, and they're making it all work. They're making it all work under budget in terms of processing power and space. We have all of the things that you don't even pay attention to, the screens on your refrigerator, your TVs, your tablets, your cars, the kiosk at McDonald's, the in-flight entertainment on the back of your plane. All of that stuff also has its own usage. Game consoles, mobile and handheld. And then you also have HPC, which is like the weather people that monitor and measure whether or not hurricanes are going to hit Corpus Christi, right? So all of this stuff is in the wheelhouse of what I'm talking about. Also want to talk about engineering progression. Typically, when you graduate, you're going to start with being just a normal run-of-the-mill engineer, and then you become a project engineer, a team engineer, a group staff engineer, and a principal engineer, okay? And so the difference is, I kind of say, engineer is you're learning how to be an engineer, and then you get pretty good, and then you become a project engineer. Now you're in charge of a larger responsibility, maybe a large portion of the hardware or the software or whatever it is you're working on. And then you're leading and you're mentoring other people and teaching them how to do what you're doing. And you're also the guy who owns it, which means that if something breaks, you're the one spending late hours to try to fix it, right? Then you have like a senior engineer, somebody who has multiple of these projects going on and orchestrating and making sure that these pieces work together, right? Then you have a staff engineer, which is saying, hey, I have this whole piece, but it's a part of a larger project or product. Now I'm working with other teams and I'm working with these people. And then finally, you have a principal engineer saying, how am I going to make the company money? And how do I reduce technical debt? And how do I make sure that everybody is doing the most with what they have and being a force multiplier, right? And being a super expert at the same time. So I would say advice on when you get a job in industry, if that's where you're going, learn as much as you can, treat every company like a university because they're all going to have different ways of doing things. And you as an engineer you're going to become the amalgamation of everywhere you've ever worked. So take the good things a la carte that you like, throw away the bad things that you don't like, and kind of evolve. Take on more responsibility. Don't get pigeonholed into one thing. If you feel like you've been doing something for too long that's not good for an engineer, you're not going to grow and thrive. Make sure you're always extending yourself and becoming uncomfortable. Contribute to the community standards. We're all open source. I write most of my code in something called Vulkan and OpenGL and OpenCL. And we go to standards committees and we meet with all the other companies. We say, what's a good idea? Is that a good idea? No, is that a good idea? And then you also make sure that your head's up, you're looking at the forest instead of just the trees. Try to understand the big picture of your company. It's going to make you more valuable. Is what you're doing important or is it not? Because if it's not important, then read the writing on the wall. Try to find an area that you love, but that's also driving revenue. And then rotate teams and positions and repeat, right? The last slide is Samsung is always hiring. We're hiring in Austin and in San Jose and in San Diego and in Folsom, all these places, and we're doing super cool stuff. And we'll open up, I think, internships in the new year, and we actually have full-time recs now.